This information is brought to you by Charles Sturt University.
Hi, this is a short video on how to do line integrals. So I want to just try this particular line integral here. So the line integral along a certain curve of z ds. And the curve is given in parametric form of x, y, z various parameters. Like at 0 to 4 pi. What this curve is, so x and y are given by cosine sine, so something with circles, and z is t. So it ends up being a, draw it properly, some sort of helix like this. So t equals 0 starts down the bottom, and t equals 4 pi is towards the top. So what this integral is trying to do is imagine that the density of this y is proportional to z. So, for example, if it's a y that is increasing thickness as you go up, then this integral would correspond to the total mass of this bit of helix. So that's what it corresponds to physically. So that's how to work it out. So when faced with these things, now just a few points. So this is a line integral. In particular, it's got a ds at the end. So line integrals with ds's are called scalar line integrals. And so for vector ones, we have a dr, or often dx, dy sort of terms cropped up, integrating along a curve. Then there are some special theorems that can apply in that situation. But when you've got just ds, then normally the best way of doing it is simply just to parameterize and effectively do integration by substitution. That normally is the preferred option to do it. So to that end, let's do it. So first of all, to work out what ds is, we need to know what dx, dy, and dz are, or the derivatives more precisely. So let's work out what x dash, y dash, and z dash are. And these are all derivatives with respect to the parameter. So in this case, the parameter is t. So x is cos, so derivative is minus sine. Derivative of sine is cos. Derivative of t is just 1. So the differential ds is pretty much given by Pythagoras' theorem. So it's the length of a little bit of curve. Is the square of all the different derivatives. So this is really just Pythagoras' theorem in disguise for all intents and purposes. So Pythagoras' theorem is sum of the squares of all different sides square rooted. That's the basic idea of Pythagoras' theorem. And so the tangent, so given what this sort of thing gives, is the direction we're looking at. But it's, anyway, so ds is the length, is the square root of sum of some squares, d, whatever the parameter is. So that's the basic way of doing the substitution. And now it's just a matter of subbing that in, all the things we know. So it's going to be minus sine squared. So the minus sign disappear when you square it. Y dash is going to be cos squared. And z dash, well, it's just 1 plus 1. Now, sine squared plus cos squared is 1, so it ends up just reducing down to square root of 1 plus 1, or root 2 dt, in this case. So now we know how to substitute the ds. The z, we just do directly. So the integral of z ds on the curve is, well, the z just becomes t. So just replace, so if it was x and y's and z's, all the different things in there, just replace them by whatever appropriate expression of everything t's. ds is, in this case, square root of 2 dt. And then the limits are going to be the limits for whatever t are. So in this case, 0 to 4 pi. For the root 2, you can just stick around the front. Doesn't really do much. Integral of t is going to be t squared on 2. And we're going to integrate it from 0 to 4 pi. Chuck in the 0, you get nothing. So in 4 pi, you're getting root 2 and 2, which is 1 on root 2. Sub in the 4 pi, you're getting, so 4 pi squared, which is 4 pi squared is 16 pi squared, all over, say, root 2, or variations thereof. And so root 2 and 2 being just 1 on root 2. And that would be the answer. So that would be the weight of this particular helix, assuming that the density increases as you go through. So just recapping, when you've got a scalar line integral, then you want to do integration by substitution effectively, and the key thing you need to do is using this transformation. So ds is equal to the square root of the sum of all the different derivatives we have with respect to the parameter. So it's only two-dimensional, you only have the first two derivatives, for example. But in this case, I've got 3 dt, and just plug that in. And otherwise, it's integration by substitution. So I hope that helps.